Tonight, we're going to explore one of the most profound discoveries in the history of science, a discovery that took a century to confirm, required the most sensitive instruments ever built by humanity, and fundamentally transformed our understanding of the cosmos. We're going to journey through the remarkable story of gravitational waves, the invisible ripples in the fabric of space-time itself that carry messages from the most violent events in the universe directly to Earth. This is a story that spans continents and generations. It begins with a young patent clerk in Switzerland who reimagined the very nature of space and time. It continues through decades of theoretical debate about whether certain mathematical solutions represented physical reality or mere abstraction. It passes through the controversial career of a pioneering experimentalist whose claims of detection were ultimately rejected, but whose persistence launched an entirely new field of physics. It reaches moments of breakthrough, the discovery of a celestial laboratory that proved gravitational waves were real, and finally, on a September morning in 2015, the first direct detection of these space-time ripples by instruments of almost inconceivable sensitivity. Along the way, we'll encounter Nobel Prize winners and unsung heroes, moments of triumph, and decades of patient waiting. We'll explore the extreme physics of neutron stars and black holes, objects so dense that they bend space-time into configurations that challenge human intuition. We'll witness the birth of multi-messenger astronomy, where gravitational waves and electromagnetic radiation combine to reveal cosmic events in unprecedented detail. And we'll look toward a future where space-based detectors and even more sensitive ground-based instruments promise to transform our understanding of the universe yet again. Before we begin this journey together, if you enjoy these deep explorations of the cosmos and how we've come to understand it, a quick like or subscribe would really help the channel continue bringing you these immersive experiences. Now let's begin our journey into the invisible symphony of the universe. Imagine standing at the edge of a still pond on a windless day. The surface is smooth, mirror-like, reflecting the sky above. Drop a pebble into the water, and ripples spread outward in expanding circles. The water itself doesn't travel with the wave. Instead, the disturbance moves through the medium, carrying energy away from the point of impact. If you watch a floating leaf near the splash, you'll see it bob up and down and side to side as each ripple passes, but the leaf doesn't move outward with the waves. It stays essentially in place while the disturbance travels past it. Now imagine something similar, but instead of water, the medium is space-time itself, the very fabric of reality that holds the entire universe together. Instead of a pebble, the disturbance comes from the collision of black holes, the explosion of massive stars, or the spiraling death dance of neutron stars. The ripples that spread outward from these cataclysmic events are gravitational waves, and they travel at the speed of light across billions of years and billions of light years to reach us here on Earth. But here's where the analogy breaks down in a profound way. Water waves need water to propagate through. Sound waves need air or some other medium. Even ocean waves stop at the shore. But gravitational waves are ripples in space-time itself. They don't need any medium because they are distortions of the medium that everything else exists within. They pass through planets, through stars, through the vast emptiness between galaxies, losing almost no energy along the way. a gravitational wave generated by a collision 1.3 billion light years away, arrives at Earth having traveled for 1.3 billion years, crossing incomprehensible distances, and yet it retains the detailed signature of the event that created it. For most of human history, we explored the universe through a single sense: sight. We looked up at the night sky and saw points of light. Ancient astronomers charted the positions of stars and tracked the wandering planets, using nothing more than their naked eyes. The invention of the telescope in the early 1600s extended human vision, revealing craters on the moon, moons orbiting Jupiter, and countless stars invisible to unaided sight. But all of this remained within the narrow band of visible light. In the 20th century, we expanded our vision beyond what human eyes could see. Radio astronomers discovered emissions from distant galaxies, from pulsars, from the cosmic microwave background radiation that fills the universe. Infrared telescopes revealed cool stars, dust clouds, and the formation of new solar systems hidden within opaque nebulae. Ultraviolet observatories studied hot stars and energetic processes that emit no visible light. X-ray and gamma-ray telescopes, necessarily launched into space to escape Earth's protective atmosphere, detected the most violent phenomena in the cosmos: black holes devouring matter, neutron stars in tight binary orbits, the aftermath of stellar explosions. Each new window on the electromagnetic spectrum revealed something new about the cosmos. The radio sky looked utterly different from the optical sky. The X-ray universe was dominated by objects barely visible at any other wavelength. Astronomers realized that the universe we see with our eyes represents only a tiny fraction of what's actually happening out there. But all of these observations shared something fundamental. They relied on light, on electromagnetic radiation in its various forms. They were all variations on the same sense, different frequencies of the same phenomenon. Gravitational waves represent something entirely different. They are not electromagnetic radiation at all. They do not travel through space-time the way light does. Instead, they are distortions in space-time, actual stretching and squeezing of the distances between objects as the wave passes through. When a gravitational wave travels through your body right now, as they constantly do, the space between your atoms literally expands and contracts, though by amounts far too small to perceive. We have, in essence, gained a new sense with which to experience the universe. We can now listen to the cosmos in a way that was literally impossible before. And what we've heard has already begun to rewrite our understanding of black holes, neutron stars, and the evolution of galaxies themselves. The story of gravitational waves stretches back more than a century, to a patent clerk in Switzerland who would become the most famous physicist in history. It winds through decades of theoretical debate, through controversial claims and failed experiments, through persistence against seemingly impossible odds, and ultimately to a moment on September 14th, 2015, when two detectors on opposite sides of the United States simultaneously recorded a signal lasting just 0.2 of a second. That brief chirp, rising rapidly in pitch before abruptly ending, was the sound of two black holes colliding 1.3 billion years ago. It was the first direct detection of gravitational waves, and it was the beginning of an entirely new era in astronomy. Part 1. Einstein's revolutionary insight. To understand gravitational waves, we must first understand the revolutionary theory that predicted their existence, Albert Einstein's general theory of relativity. And to appreciate the magnitude of that revolution, we need to step back even further to the understanding of gravity that prevailed before Einstein transformed physics. For more than 2 centuries, Isaac Newton's theory of gravity dominated scientific thinking. Published in his Principia Mathematica in 1687, Newton's framework described gravity as a force that acts instantaneously across any distance. Every object with mass attracts every other object with mass. The sun pulls on the earth, and the earth pulls on the sun. The strength of this attraction depends on the masses involved and the distance between them, following Newton's famous inverse square law. This framework worked extraordinarily well. It explained the orbits of planets, predicted the existence of Neptune based on perturbations in the orbit of Uranus, and formed the foundation of celestial mechanics. Engineers used Newtonian gravity to calculate the trajectories of cannonballs, the paths of comets, and eventually the orbits of artificial satellites. But Newton's theory had a conceptual problem, one that troubled Newton himself throughout his life. How exactly does the sun know that the Earth is there, 150 million kilometers away? How does the gravitational influence travel from one body to another? If some cosmic event suddenly changed the sun's mass, would Earth immediately feel the difference, even though light from the sun takes 8 minutes to reach us? Newton's equations implied yes, the effect would be instantaneous, a troubling concept that seemed to violate any reasonable understanding of causality. Newton famously wrote that he feigned no hypotheses about the mechanism of gravity's action at a distance. He acknowledged the problem, but declined to speculate about solutions. The mathematical framework worked, and that would have to be enough. Philosophers and scientists debated the issue for 2 centuries. Various proposals were floated, including the notion that some invisible medium pervaded all of space and transmitted gravitational influence. But none of these proposals had predictive power that could be tested against observation. Einstein provided the answer, and in doing so completely overturned our understanding of space, time, and gravity itself. In November 1915, Einstein presented his general theory of relativity to the Prussian Academy of Sciences. The theory emerged from a decade of struggle, during which Einstein wrestled with the mathematics of curved space-time and repeatedly encountered dead ends. The final version came together in a frantic few weeks in November 1915, with Einstein racing against mathematician David Hilbert, who was working on similar ideas. The theory was revolutionary in several respects. Most fundamentally, it reimagined gravity not as a force acting through space, but as a consequence of the curvature of space-time itself. In Einstein's conception, massive objects warp the fabric of space-time around them. The sun creates a depression in space-time, and the Earth rolls around the edge of that depression in what appears to us as an orbit. There is no mysterious force reaching across the void. Instead, objects follow the straightest possible paths through curved space-time, paths called geodesics. What we perceive as the force of gravity is really the geometry of the universe itself guiding the motion of matter. This insight had immediate and testable consequences. Einstein predicted that light passing near a massive object would bend, following the curved space-time around it. During the total solar eclipse of May 29, 1919, British astronomer Arthur Eddington led expeditions to observe stars whose light passed near the sun during the eclipse. The stars appeared slightly displaced from their expected positions by amounts consistent with Einstein's predictions. The confirmation made Einstein an international celebrity and general relativity the new framework for understanding gravity. But there was another prediction embedded in Einstein's equations, one that would take a century to confirm directly. If massive objects warp space-time around them, then accelerating massive objects should create ripples in that curvature that propagate outward at the speed of light. These ripples are gravitational waves. Einstein first predicted the existence of gravitational waves in a paper published in June 1916, just months after completing the general theory of relativity. He calculated that a system of masses accelerating relative to each other would emit gravitational radiation, carrying energy away from the system. The analogy with electromagnetic radiation was clear. Just as accelerating electric charges produce electromagnetic waves, accelerating masses produce gravitational waves. However, there were crucial differences. Electromagnetic waves are emitted whenever charges accelerate, but most everyday accelerations produce utterly negligible gravitational radiation. Even the motion of massive objects in our solar system generates gravitational waves of impossibly small amplitude. Einstein calculated that for gravitational waves to be detectable, you would need not just massive objects, but objects accelerating extremely rapidly on the scale of astronomical cataclysms. Einstein himself was uncertain about the physical reality of gravitational waves. In 1936, he and his assistant Nathan Rosen submitted a paper to Physical Review arguing that gravitational waves do not exist, that they were merely mathematical artifacts of his equations rather than physical phenomena. The journal sent the paper to a referee, Howard Percy Robertson, who identified errors in Einstein and Rosen's analysis. Einstein, unaccustomed to peer review, angrily withdrew the paper, but after further consideration, and after his assistant Leopold Infeld independently discovered the same errors, Einstein reversed his position. The corrected paper, published in the Journal of the Franklin Institute in 1937, acknowledged that gravitational waves were indeed real solutions to the field equations of general relativity. Even after accepting their mathematical existence, physicists debated for decades whether gravitational waves carried real energy. Could they actually do work on matter, or were they merely coordinate effects that could be transformed away by choosing a different reference frame? Arthur Eddington famously quipped that gravitational waves travel at the speed of thought, suggesting they might be more mathematical fiction than physical reality. The debate was largely resolved at a 1957 conference in Chapel Hill, North Carolina. There, the legendary physicist Richard Feynman presented what became known as the sticky bead argument. Imagine a rod with beads on it that can slide freely along the rod, but experience friction as they move. If a gravitational wave passes perpendicular to the rod, it will alternately stretch and compress the rod. The beads will slide back and forth, and the friction will generate heat. Since heat is energy, the gravitational wave must carry energy. This elegant thought experiment convinced most physicists that gravitational waves were physically real and could, in principle, be detected. But principle and practice are very different things. The fundamental challenge is that gravity is the weakest of the four fundamental forces by an almost incomprehensible margin. The gravitational force between two protons is about 10 to the power of 36 times weaker than the electromagnetic force between them. This weakness is why we don't notice the gravitational attraction between everyday objects, only the cumulative attraction of enormous masses like planets and stars. This extreme weakness means that gravitational waves interact very feebly with matter. A gravitational wave passes through almost everything with barely any effect at all. The Earth is essentially transparent to gravitational waves. Your body is transparent to gravitational waves. The entire planet provides no shielding whatsoever. On one hand, this means gravitational waves can carry information from deep inside violent events that would absorb all electromagnetic radiation. The interior of a supernova, the moment of black hole formation, the instant before two neutron stars collide. These are hidden from any electromagnetic telescope, but open to gravitational wave detection. On the other hand, the same transparency that allows gravitational waves to escape from these events also makes them extraordinarily difficult to detect. Consider what happens when a gravitational wave passes through you. The wave alternately stretches space in one direction while compressing it in the perpendicular direction. Your body, sitting in that space, is stretched and squeezed along with it, but because everything around you, including the ruler you might use to measure these changes, is stretched and squeezed in the same way, you have no reference point to notice the effect. It's like trying to measure the expansion of the universe with a ruler that expands at the same rate. To detect gravitational waves, you need to exploit the subtle difference in how the wave affects objects in different orientations and how light travels through the distorted spacetime. This required entirely new approaches to measurement, approaches that pushed technology to its absolute limits. And it required patience measured in decades. Part 2. The Pioneer's Quest. In the 1950s and 1960s, while most physicists considered gravitational wave detection to be a hopeless dream, one man dedicated his career to making it reality. Joseph Weber, a physicist at the University of Maryland, would become the founding father of experimental gravitational wave research, even though his own attempts at detection remain controversial to this day. Weber had led an unconventional life before becoming a physicist. Born in 1919 in Paterson, New Jersey, to Yiddish-speaking immigrant parents who had fled persecution in Eastern Europe, he grew up in difficult circumstances. His birth name was Yonah, later Americanized to Joseph. When he was 5 years old, he was struck by a bus and suffered injuries that temporarily robbed him of the ability to speak. After learning to talk again through speech therapy, his Yiddish-influenced accent was gone, replaced by the Middle American diction of his therapist. Weber joined the United States Navy at a young age and became a communications officer, developing expertise in electronics and radio technology. During World War II, he served aboard the aircraft carrier USS Lexington and survived its sinking at the Battle of the Coral Sea on May 8, 1942. The Lexington was hit by multiple Japanese torpedoes and bombs during the battle. Weber was among the roughly 2,700 crew members who survived the sinking. 216 others perished. The experience of surviving such a catastrophe, combined with his technical training, shaped Weber's character. a combination of bold ambition and meticulous attention to detail that would define his scientific career. After the war, he earned a PhD in physics from Catholic University while working as an electrical engineering professor at the University of Maryland. His doctoral work focused on atomic physics, and he drew on his naval experience with microwaves to develop new theoretical insights. Weber's early work focused on microwave physics. He was among the first to describe the theoretical principles behind the maser, a precursor to the laser that amplifies microwave radiation through stimulated emission. In 1952, he gave a public lecture in Ottawa outlining the concept. Charles Townes, Nikolai Basov, and Alexander Prokhorov would later win the 1964 Nobel Prize in Physics for developing masers and lasers, work that overlapped substantially with Weber's ideas. Some have suggested Weber deserved recognition for his contributions to this field as well, though the history of who developed what first remains somewhat contested. But Weber's true passion lay in general relativity and gravitational radiation. During a sabbatical in 1955 and 1956, funded by a Guggenheim Fellowship, he studied with John Wheeler at Princeton, one of the foremost relativists of the era. Wheeler, who would later coin the term black hole, was deeply interested in the physical reality of gravitational waves and encouraged Weber's thinking about detection methods. Wheeler later wrote about Weber's enthusiasm for the quest, noting that he embraced gravitational waves with religious fervor. At the 1957 Chapel Hill Conference, Weber heard Feynman's sticky bead argument firsthand. He became convinced that gravitational waves not only existed, but could be detected with sufficiently clever instrumentation. Weber's approach was elegant in its simplicity, though fiendishly difficult in practice. He proposed using large, aluminum cylinders, several meters long and about a meter in diameter, as gravitational wave antennas. When a gravitational wave passed through such a cylinder, it would alternately stretch and squeeze the metal along its length. The effect would be extraordinarily small, far smaller than any human could perceive. But if the frequency of the wave matched the natural resonant frequency of the cylinder, around 1,660 Hertz. For his initial design, the vibrations would build up through resonance, much as a singer's voice can shatter a glass at its resonant frequency. By monitoring the cylinder with sensitive piezoelectric crystals capable of converting mechanical stress into electrical signals, Weber hoped to detect the tiny vibrations induced by passing gravitational waves. These devices became known as Weber bars. Weber published his first paper on the detection concept in 1959, followed by a second paper the next year. In 1961, he joined the University of Maryland Physics Department as a full professor and set about constructing actual detectors. His laboratory became filled with massive aluminum cylinders, electronics, and recording equipment. The cylinders had to be isolated from environmental vibrations, which meant suspending them on wires and placing them inside vacuum chambers. Temperature fluctuations could cause the metal to expand and contract, masking any gravitational signal, so thermal stability was essential. Weber constructed his first prototype in 1960 and spent years refining the design and sensitivity. By 1965, he had operational detectors at his laboratory at the University of Maryland. He placed additional detectors at Argonne National Laboratory near Chicago, about 1,000 kilometers away, with one detector housed in a makeshift garage about a mile from the main campus. The idea was to look for coincident signals, vibrations detected at both locations simultaneously. Since gravitational waves travel at the speed of light and would affect widely separated detectors nearly simultaneously, coincident signals would be strong evidence for actual gravitational wave detection, as opposed to local noise sources like passing trucks, electrical interference, or minor earthquakes that would affect only one detector. Weber developed his own statistical algorithms to analyze the data, comparing the signals from his detectors and looking for correlations that exceeded what would be expected from random noise. His methods were innovative, but would later prove controversial, as other scientists questioned whether he had properly accounted for all sources of systematic error. In 1969, at a general relativity conference, Weber made a stunning announcement. He had detected gravitational waves. He claimed to have observed dozens of coincident events over an 81-day observation period. The scientific world was electrified. If true, this would be one of the most important physics discoveries of the century, definitive proof of Einstein's century-old prediction. Weber published his results in Physical Review Letters, the premier physics journal. He claimed to observe roughly one event per day, with the signals apparently correlated with the direction toward the center of our galaxy. This suggested the source might be violent events near the massive black hole at the Milky Way's core, which we now call Sagittarius, a star. In 1970, he published additional results, claiming more than 300 coincident events over 7 months. The response from the scientific community was initially enthusiastic, but soon turned skeptical. The problem was that other groups could not reproduce Weber's results. Scientists at IBM, Stanford, Bell Labs, Oxford, Cambridge, and institutions across Europe built their own Weber bars, sometimes with improved sensitivity. None of them detected anything beyond random noise. The theoretical predictions were also problematic. If Weber really was detecting gravitational waves at the rate he claimed, the sources would have to be extraordinarily powerful. Richard Garwin, a physicist at IBM who built one of the most sensitive competing detectors, calculated that Weber's claimed detection rate would require the galaxy to be converting all its mass into gravitational wave energy within about 50 million years. An obviously impossible scenario. The galaxy would essentially be tearing itself apart. A pivotal confrontation occurred at an MIT conference in June 1974. Garwin publicly challenged Weber's results, pointing to specific problems with his analysis methods. David Douglas, another physicist, had identified what he believed was an error in Weber's computer algorithms. Weber had apparently allowed for noise with random amplitude, but had not properly accounted for random phase. This meant that spurious signals could appear to emerge from the noise, even when no real signal was present. Weber defended his work vigorously until his death in September 2000. He never accepted that his detections were spurious and continued to publish papers claiming positive results, even as the scientific consensus turned against him. The situation became a cautionary tale in the physics community about the dangers of confirmation bias and the importance of independent replication. And yet Weber's legacy is far more nuanced than simple failure. At the very announcement of the first LIGO detection in February 2016, speakers went out of their way to honor Weber as the founding father of the field. Kip Thorne, who would share the Nobel Prize for LIGO, described Weber as the pioneer who started all of this. Weber's notebooks contained ideas for laser interferometry that would eventually evolve into LIGO's design. His student Robert Forward built the first laser interferometer gravitational wave detector at Hughes Research Laboratories. Weber was, by all available evidence, wrong about detecting gravitational waves with his bars. His claimed signals appear to have been artifacts of his analysis methods rather than genuine astrophysical events. But he was absolutely right that gravitational waves could be detected, and he inspired an entire generation of scientists to take up the challenge. Sometimes the most important contribution a scientist can make is to demonstrate that a seemingly impossible problem is worth pursuing at all. Based on his work and the intellectual framework he established, the field gradually evolved toward more sensitive techniques that would eventually succeed where his original approach fell short. Part 3. Indirect evidence from the cosmic laboratory. While Weber's claims sparked controversy, evidence for gravitational waves was accumulating from an entirely different direction. In 1974, two radio astronomers discovered a celestial object that would become one of the most important laboratories in all of physics, providing the first compelling evidence that gravitational waves are real. Russell Hulse was a graduate student at the University of Massachusetts, working under the supervision of Joseph Taylor. Their project involved using the Arecibo radio telescope in Puerto Rico to search for pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the neutron star rotates, these beams sweep through space like lighthouse beams, producing regular pulses of radio emission when they point toward Earth. Neutron stars themselves are among the most extreme objects in the universe. They form when massive stars, those with at least about 8 times the mass of our Sun, exhaust their nuclear fuel and collapse. Throughout their lives, massive stars burn through successive layers of fuel. Hydrogen fuses to helium, helium to carbon and oxygen, and in the most massive stars, fusion continues through neon, oxygen, silicon, and finally iron. But iron is a dead end. Fusing iron absorbs energy rather than releasing it. When the core becomes dominated by iron, nuclear fusion can no longer support the star against gravity. The core collapses in less than a second. The outer layers of the star, no longer supported, fall inward at a significant fraction of the speed of light. When the collapsing core reaches nuclear density, it bounces back, sending a shock wave outward that tears the star apart in a supernova explosion. The outer layers are blasted into space, seeding the interstellar medium with heavy elements. But the core itself is left behind, compressed so dramatically that protons and electrons are crushed together through a process called inverse beta decay to form neutrons. This is our current understanding of the mechanism, though the precise details of how the shock wave revives and propagates remain an active area of research. The resulting object contains more mass than our Sun compressed into a sphere, only about 20 kilometers across, roughly the size of a city. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravitational field at the surface is so intense that the escape velocity approaches a significant fraction of the speed of light. An object dropped from 1 meter above the surface would hit the star traveling at about 2,000 kilometers per second. The surface gravity is about 200 billion times stronger than Earth's. If you somehow stood on a neutron star, you would be instantly crushed into a thin smear of matter. Inside a neutron star, the physics becomes even more exotic. The outer crust is thought to consist of a lattice of iron group nuclei, but deeper down, nuclei become increasingly neutron-rich and eventually dissolve into a fluid of neutrons. Based on theoretical models and what we can infer from observations, the core may contain exotic forms of matter, hyperons, free quarks, or Bose-Einstein condensates of pions or kaons. The equation of state, the relationship between pressure and density inside a neutron star, remains one of the major unsolved problems in nuclear physics. Gravitational wave observations of neutron star mergers are beginning to constrain these possibilities by revealing how neutron stars deform under tidal forces as they approach each other. When neutron stars rotate rapidly and possess strong magnetic fields, they become pulsars. The rotation periods can be extraordinarily stable, rivaling or exceeding the best atomic clocks. Millisecond pulsars, which spin hundreds of times per second, are particularly stable, having been spun up by accretion from companion stars in binary systems. This stability makes pulsars excellent cosmic timekeepers. By carefully tracking the arrival times of pulses over months and years, astronomers can detect extremely subtle changes in the pulsar's motion. On July 2, 1974, Holtze was analyzing data from a systematic pulsar survey when he noticed something unusual. One of the new pulsars he had discovered, designated PSRB 1913+16, showed peculiar behavior. Its pulse period wasn't constant, but varied in a regular pattern over about 7.75 hours. The period shortened, then lengthened, then shortened again. Following a predictable cycle, Holtze quickly realized what this meant. The pulsar was in orbit around another object. When the pulsar moved toward Earth in its orbit, its pulses were slightly blue-shifted, arriving closer together. When it moved away, the pulses were red-shifted, arriving farther apart. The variation in pulse timing was a direct measurement of the pulsar's orbital motion. Further analysis revealed that the companion object was itself extremely compact. The orbital dynamics strongly suggested another neutron star, though the data alone couldn't entirely rule out a massive white dwarf or even a black hole. However, given that neutron stars form in supernova explosions and the system's characteristics align with what we'd expect from a double neutron star system, most astronomers accept this as the most straightforward interpretation. This discovery, the first known binary pulsar, was immediately recognized as extraordinary. Here was a system of two extremely dense objects in a tight orbit around their common center of mass. The orbital period was just 7.75 hours, meaning the stars completed a full orbit in less than a single workday. The orbit was highly elliptical, bringing the stars as close as about 1.1 solar radii at their closest approach, and separating them by about 4.8 solar radii at their farthest. These extreme conditions made the system a perfect laboratory for testing general relativity. Taylor continued observations of the binary pulsar for years after Holtze graduated. The precision of pulsar timing allowed measurement of relativistic effects impossible to detect in any Earth-based laboratory. The orbit precessed, meaning the orientation of the ellipse slowly rotated by about 4.2 degrees per year. This is an enormous amount compared to the precession of Mercury's orbit, which amounts to only 43 arcseconds per century, and was one of the first confirmations of general relativity. The binary pulsar's precession agreed precisely with Einstein's predictions, but the most important measurement concerned the orbital period itself. Over years of observation, Taylor detected that the orbit was shrinking. The two neutron stars were spiraling closer together, completing each orbit slightly faster than the previous one. The orbital period was decreasing by about 76 millionths of a second per year. This might seem tiny, but over decades of observation, the cumulative effect was unmistakable. General relativity predicts exactly this behavior. As the neutron stars orbit each other, they emit gravitational waves. These waves carry energy away from the system. As the system loses energy, the stars fall into tighter orbits, moving faster. This is precisely analogous to how satellites in low Earth orbit gradually fall closer to Earth as they lose energy to atmospheric drag, except the binary pulsar is losing energy to gravitational radiation rather than friction. Taylor and his colleagues compared the observed orbital decay to the prediction of general relativity with exquisite precision. The agreement was remarkable. The observed decay rate matched the theoretical prediction to within about 0.2%. As observations continued over decades, the agreement improved further. By the early 2000s, the match was better than 99.8%. This was indirect evidence for gravitational waves, but it was overwhelming evidence nonetheless. There was no known mechanism other than gravitational wave emission that could account for the orbital decay. The energy had to be going somewhere, and gravitational waves were the only explanation consistent with general relativity. Based on these observations, combined with our understanding of binary stellar dynamics, we can be confident that the energy loss is attributable to gravitational radiation. In 1993, Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics for the discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation. The Nobel Committee explicitly cited the gravitational wave implications of the binary pulsar observations. Einstein's prediction, made 77 years earlier, had been confirmed. Since then, additional binary pulsars have been discovered, including systems where both neutron stars are detectable as pulsars. These double pulsar systems provide even more stringent tests of general relativity. In every case, the orbital evolution matches the predictions of gravitational wave emission. The evidence is now so overwhelming that the existence of gravitational waves became accepted scientific fact even before the first direct detection. The binary pulsar observations also allowed astronomers to predict the ultimate fate of such systems. As the neutron stars spiral closer together, the orbital period decreases and the gravitational wave emission intensifies. Eventually, the stars will merge in a cataclysmic collision. For the Hulse-Taylor pulsar, based on the observed rate of orbital decay, this merger will occur in roughly 300 million years. When it happens, the final moments will produce gravitational waves powerful enough to be detected by instruments on Earth, if any such instruments exist that far in the future. Part 4. Building the Impossible. While the binary pulsar provided compelling indirect evidence for gravitational waves, the scientific community yearned for direct detection, feeling the waves themselves, rather than inferring their existence from orbital dynamics, would open entirely new windows on the universe. But achieving this required pushing measurement technology to seemingly impossible limits. The key insight that would eventually make detection possible came from a physicist named Rainer Weiss. Born in Berlin in 1932, Weiss came to the United States as a child when his family fled Nazi Germany. He studied physics at MIT and joined the faculty there in 1962. His early career focused on atomic physics and precision measurements, skills that would prove essential for gravitational wave detection. In 1967, Weiss was teaching a course on general relativity at MIT. While preparing lectures, he began thinking seriously about gravitational wave detection. He was aware of Weber's work with resonant bars, but saw fundamental limitations with that approach. Weber bars were sensitive only to gravitational waves at their specific resonant frequency. Any signal at a different frequency would be missed. What was needed was a broadband detector that could respond to a wide range of frequencies. Weiss proposed using laser interferometry. The concept was elegant. Split a laser beam into two perpendicular arms, reflect the beams back from mirrors at the end of each arm, and recombine them. If both arms are exactly the same length, the light waves will interfere in a predictable way. But if a gravitational wave passes through, stretching one arm while compressing the other, the interference pattern will shift slightly. By measuring this shift with extreme precision, you could detect the passage of the wave. In 1972, Weiss wrote a detailed technical study laying out the requirements for a laser interferometer gravitational wave detector. The document, buried as a quarterly progress report to MIT's funding agencies, became a foundational text for the field. Weiss analyzed every source of noise that could mask a gravitational wave signal: seismic vibrations from the Earth, thermal fluctuations in the mirrors, quantum noise in the laser light, acoustic disturbances in the air. For each noise source, he proposed solutions or calculated how large the detector would need to be to overcome it. The numbers were daunting. To detect gravitational waves from plausible astronomical sources, an interferometer would need arms several kilometers long. It would need to measure changes in length of less than 1/10,000th the diameter of a proton. This is equivalent to measuring the distance to the nearest star and detecting a change smaller than the width of a human hair. The precision required was almost beyond comprehension. Around the same time, theoretical physicist Kip Thorne at Caltech was becoming increasingly interested in gravitational waves. Thorne had studied under John Wheeler, the same mentor who had encouraged Joseph Weber. He had made important contributions to the theory of black holes and relativistic astrophysics. In the early 1970s, he began to believe that gravitational wave detection was not only possible, but could transform astronomy. Thorne's theoretical work helped identify what sources might be detectable. The most promising were compact binary systems, pairs of neutron stars or black holes spiraling together. In the final moments before merger, such systems would emit gravitational waves at frequencies and amplitudes that an Earth-based interferometer could detect. if the interferometer were sensitive enough. The paths of Weiss and Thorne converged in 1975 when they met at a NASA conference in Washington, D.C. They discussed their respective visions for gravitational wave detection and found their approaches complementary. Weiss focused on experimental techniques, Thorne on theoretical predictions of what the instruments might see. They began collaborating, initially informally, and then with increasing intensity. In 1984, the National Science Foundation funded a joint Caltech-MIT project to design and construct a major gravitational wave observatory. The project was named LIGO, the Laser Interferometer Gravitational Wave Observatory. The initial proposal called for two identical detectors separated by thousands of kilometers. The separation served two purposes. It would allow genuine gravitational wave signals to be distinguished from local noise by requiring coincident detection at both sites, and it would enable rough localization of sources in the sky based on the slight time difference between signal arrivals. The early years of LIGO were marked by both progress and turmoil. The technical challenges were enormous, and the project management proved difficult. By the early 1990s, LIGO was falling behind schedule and over budget, a common fate for ambitious physics experiments, but a dangerous situation when dealing with skeptical funding agencies. Enter Barry Barish, a particle physicist at Caltech. Barish had managed the construction of major detector systems for high-energy physics experiments. In 1994, he was brought in to lead LIGO. Barish immediately recognized that the project needed to be reorganized as a major collaborative effort involving scientists from around the world, not just Caltech and MIT. He transformed LIGO into the LIGO Scientific Collaboration, eventually involving more than 1,000 scientists from dozens of institutions across multiple countries. Barish also made the crucial decision to build LIGO in two phases. Initial LIGO would use the best available technology and would most likely not detect gravitational waves. Instead, it would serve as a proof of concept, demonstrating that the basic approach worked and identifying which noise sources needed to be addressed. Advanced LIGO would incorporate improved technology and would have a realistic chance of detection. This staged approach was essential for maintaining funding and momentum. If LIGO had promised detection and then failed, the project might have been canceled. By framing initial LIGO as a technology development program with a clear upgrade path, Barish kept expectations realistic while maintaining the ultimate goal. Construction of the two LIGO facilities began in 1994, with groundbreaking ceremonies that few outside the gravitational wave community noticed. One detector was built near Livingston, Louisiana, in a rural area surrounded by pine forests. The site was chosen partly for its relative geological stability, but also because the flat terrain of Louisiana made it easier to construct straight, level arms extending for kilometers. The other was built near Hanford, Washington, on the Department of Energy's Hanford Nuclear Reservation, a vast area of desert that had been used for plutonium production during the Cold War and remained largely empty. The sites were chosen for their relative seismic stability and their separation of about 3,000 kilometers, which would provide a baseline for determining signal arrival times and distinguishing real gravitational waves from local disturbances. Building these detectors required solving problems that had never been faced before. The vacuum system alone was an engineering marvel. 16,000 cubic meters of volume pumped down to 1/1,000,000th of atmospheric pressure, one of the largest ultra-high vacuum systems ever constructed. The vacuum tubes themselves, 1.2 meters in diameter and stretching 4 kilometers through the Louisiana pines and Washington desert, had to be manufactured, transported, welded together on site, and sealed against any possible leaks. A single fingerprint left inside the tube could outgas enough molecules to ruin the vacuum. Each facility features 2 perpendicular arms, each 4 kilometers long. The arms are vacuum tubes about 1.2 meters in diameter, pumped down to 1/1,000,000th of atmospheric pressure to eliminate interference from air molecules. This vacuum is more complete than the space between planets in our solar system. Without this extreme vacuum, residual gas molecules would scatter the laser light and introduce noise that would swamp any gravitational wave signal. At the ends of each arm are massive mirrors, weighing about 40 kilograms each, suspended as pendulums, to isolate them from seismic vibrations. These mirrors are not ordinary optical components. They are made from ultra-pure fused silica, specifically manufactured to minimize internal defects that could scatter light. The surfaces are polished to atomic smoothness, with irregularities measured in angstroms. The coatings that make them reflective are deposited in specialized facilities with contamination controls, rivaling those used in semiconductor manufacturing. Even microscopic dust particles on the mirror surface would scatter light and introduce noise. The suspension systems that hold the mirrors are engineering marvels in their own right. Each mirror hangs from a chain of pendulums, with each stage filtering out vibrations at different frequencies. The final suspension stage uses thin fibers of fused silica, the same material as the mirror itself, fused directly to the substrate. These glass fibers have extremely low mechanical loss, meaning they don't dissipate energy through internal friction the way metal wires would. This reduces thermal noise, random fluctuations caused by the microscopic jiggling of atoms at room temperature. The laser system at the heart of LIGO is a marvel of engineering. A continuous laser beam is split at a beam splitter, sending half down each arm. The beams travel to the end mirrors, bounce back, and recombine at the beam splitter. In their normal configuration, the beams are set up so that when they recombine, they destructively interfere, canceling each other out and leaving no light for the detector. Any change in the relative lengths of the arms shifts this interference pattern, allowing some light through. The detector measures this light with exquisite precision, converting photon counts into information about arm length changes. To increase sensitivity, LIGO uses a technique called Fabry-Perot cavities. Additional partially reflecting mirrors near the beam splitter cause the laser light to bounce back and forth multiple times in each arm before exiting. This effectively increases the arm length by about 300 times without actually building longer arms. The result is that the laser light travels about 1,200 kilometers in each arm before returning to the beam splitter. Even with these enhancements, the signals are incredibly faint. LIGO must detect changes in arm length of about 10 to the negative 19 meters, roughly 1/10,000th the diameter of a proton. To achieve this, the mirrors must be almost perfectly still. Seismic isolation systems suspend the mirrors on multiple stages of pendulums, filtering out ground vibrations. Active feedback systems use sensors to detect any remaining motion and apply correcting forces. Initial LIGO began operation in 2002 and continued through 2010. As expected, it made no detections. However, it achieved its design sensitivity and demonstrated that the basic concept worked. The data was analyzed exhaustively, and upper limits on gravitational wave emission from various sources were established. Just as importantly, the initial LIGO period allowed scientists to identify which improvements would be most effective. The upgrade to advanced LIGO began immediately after initial LIGO ended. The improvements were comprehensive: new suspensions for the mirrors, improved seismic isolation, more powerful lasers, larger mirrors made from ultra-pure fused silica, and new optical configurations to reduce quantum noise. Each improvement addressed a specific limitation identified during initial LIGO operation. By September 2015, advanced LIGO was nearing the end of its upgrade process. The detectors had been brought back online for an engineering run, essentially a final tune-up before official scientific observations would begin. Scientists were making adjustments, checking calibrations, and running tests. They did not expect to see anything interesting yet. They were wrong. Part 5. The Day We Heard the Universe. September 14th, 2015 began as an ordinary Monday in Louisiana and Washington. At the LIGO Livingston Observatory, the detector was operating quietly in its concrete building surrounded by pine forests. At LIGO Hanford, the situation was similar. Another day of engineering work, monitoring screens, and adjustment. At 5:51 in the morning, Eastern Daylight Time, 4:51 a.m. Central Time, in Louisiana, the Livingston detector registered something unusual. A signal swept through the interferometer, rising rapidly in frequency from about 35 Hz to about 250 Hz in just 0.2 of a second, then abruptly cutting off. 7 milliseconds later, the Hanford detector recorded essentially the same signal. The signal had a very distinctive shape, a characteristic chirp that rose in both frequency and amplitude before suddenly stopping. This was exactly what theory predicted for the final moments of two black holes spiraling together and merging. As the black holes orbit each other faster and faster, the gravitational waves they emit have correspondingly higher frequencies. The amplitude increases as the objects approach each other. Then, at the moment of merger, the signal peaks and rapidly dies away as the newly formed black hole settles into a stable configuration. The signal was so clear, so close to what the theoretical templates predicted, that some scientists initially suspected it might be a fake. LIGO had a system for injecting fake signals into the data stream as a way to test the detection algorithms and the collaboration's response. These blind injections were kept secret from most of the collaboration until the analysis was complete. Was this one of those? It wasn't. The LIGO leadership quickly confirmed that no blind injection had been planned. The signal, designated GW150914 for the date of its detection, was real. After more than a century of searching, gravitational waves had been directly detected for the first time, but the collaboration did not rush to announce. Science demands rigor, especially for a discovery of this magnitude. For the next 5 months, hundreds of scientists analyzed the data from every conceivable angle. They checked for instrumental artifacts, examined the coincidence between detectors, compared the signal to theoretical templates, calculated statistical significance, and cross-checked their work in every way they could devise. The analysis revealed the nature of the source. GW150914 came from two black holes, one about 36 times the mass of the Sun, and the other about 29 times. They were orbiting each other at about 250 kilometers per second, nearly half the speed of light, in the final moments before merger. The collision occurred about 1.3 billion light-years from Earth, meaning the signal had traveled for 1.3 billion years before reaching LIGO. In the final fraction of a second before merger, the two black holes released an almost incomprehensible amount of energy. About 3 solar masses worth of matter was converted entirely into gravitational wave energy, following Einstein's famous equation E equals mc squared. For a brief moment, the collision was emitting more energy than all the stars in the observable universe combined. This energy was carried away by the gravitational waves that spread outward at the speed of light, eventually reaching Earth 1.3 billion years later. The statistical significance of the detection was overwhelming. Scientists calculated that the probability of random noise producing such a clear signal coincident in both detectors was less than 1 in 200,000 years of observation. In the language of physics, this was a 5 sigma detection, the gold standard for claiming discovery. On February 11, 2016, the LIGO Scientific Collaboration held a press conference to announce the detection. The event, held simultaneously at the National Press Club in Washington, D.C., and at numerous satellite locations around the world, drew extraordinary media attention. The paper describing the discovery was published that same day in Physical Review Letters, the same journal where Joseph Weber had published his controversial claims nearly half a century earlier. The announcement made front-page news worldwide. Einstein's 1916 prediction had been confirmed directly. A new era in astronomy had begun, and scientists now had a tool to study phenomena that had been completely invisible before. The discovery triggered an outpouring of scientific papers analyzing the implications. The masses of the merging black holes were larger than expected, suggesting that the population of stellar mass black holes in the universe was more diverse than previously thought. Based on what we can infer from this single detection combined with our theoretical understanding of black hole formation, the progenitor stars likely formed in an environment with lower metallicity than our Sun, allowing them to retain more mass at the end of their lives. The detection rate, even from just this one event, suggested that black hole mergers might be more common than some models predicted. In October 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. The prize recognized both the experimental achievement of building a detector sensitive enough to see gravitational waves and the theoretical work that predicted what the detector would find. At the ceremony, speakers repeatedly acknowledged Joseph Weber as the founding father of the field, even though his own detection claims remained controversial. The first detection was just the beginning. Between September 2015 and January 2016, LIGO's first observing run detected 2 more likely gravitational wave events. The second observing run, from November 2016 to August 2017, detected several more. With each detection, our understanding of the gravitational wave universe deepened. Part 6. Fire and Gold. The third observing run of advanced LIGO began in April 2019 and continued with interruptions through March 2020. By this point, detection of binary black hole mergers had become almost routine. Dozens had been observed, and each added to our statistical understanding of black hole populations. But one detection from an earlier run had already transformed astronomy in a way that went far beyond black holes. On August 17, 2017, at 12:41:04 Universal Time, the LIGO and Virgo detectors simultaneously observed a gravitational wave signal. Unlike the previous detections, which lasted only fractions of a second, this signal persisted for about 100 seconds, gradually sweeping up in frequency. The longer duration indicated that the merging objects were less massive than black holes. They were neutron stars. The detection, designated GW170817, represented the first observation of a binary neutron star merger. The two neutron stars, each containing about 1.1 to 1.6 times the mass of the Sun, compressed into a sphere about 20 kilometers across, had been spiraling together for millions of years. In their final minutes, they orbited faster and faster, emitting increasingly powerful gravitational waves. At last, they touched, merged, and based on what we can determine from the combined mass of the system, most likely collapsed into a black hole. But something else happened at that moment, something that electromagnetic telescopes could see. About 1.7 seconds after the gravitational wave signal peaked, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same region of sky. Gamma ray bursts had been observed for decades. Mysterious flashes of the highest energy radiation from seemingly random locations in the cosmos. Some had been associated with supernovae, but others remained unexplained. The coincidence in time and location between the gravitational wave signal and the gamma ray burst strongly suggested a connection. Within hours, telescopes around the world were pointing at the region of sky indicated by the gravitational wave detection. The signal had been observed by 3 detectors: LIGO Livingston, LIGO Hanford, and Virgo in Italy, allowing reasonably precise localization. Astronomers identified a new point of light in the galaxy, NGC 4993, about 130 million light-years away. This was the electromagnetic counterpart to the gravitational wave source. What followed was the most comprehensive astronomical observation campaign in history. Over the following weeks, more than 70 observatories on all 7 continents and in space observed the event across the entire electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each wavelength revealed different aspects of the cataclysm. The visible light observations showed something remarkable. The point of light initially glowed blue, but rapidly reddened over the following days. This color evolution matched theoretical predictions for a kilonova, an explosion powered by the radioactive decay of heavy elements freshly synthesized in the merger. For decades, astronomers had wondered where the heaviest elements in the universe come from. Elements up to iron can be made in the cores of ordinary stars through nuclear fusion, a process called stellar nucleosynthesis. Hydrogen fuses to helium, releasing energy. Helium fuses to carbon and oxygen. In massive stars, this process continues through neon, oxygen, silicon, and finally iron. Each step releases energy that supports the star against gravitational collapse. But creating elements heavier than iron requires a different process: rapid neutron capture, known as the R process. In this process, atomic nuclei absorb neutrons faster than they can decay through beta emission, building up to heavy elements like gold, platinum, and uranium. The process was first described by physicists Margaret and Geoffrey Burbidge, William Fowler, and Fred Hoyle in their landmark 1957 paper, sometimes called B2FH, after their initials. They established the theoretical framework for understanding how elements are synthesized in stars. The R process requires an environment flooded with free neutrons at densities and temperatures far beyond what ordinary stars can provide. For decades, the leading candidate for R process sites was core collapse supernovae, the explosive deaths of massive stars. The intense neutrino flux from a collapsing stellar core could, in theory, drive conditions favorable for rapid neutron capture, but calculations proved difficult, and astronomers weren't certain whether supernovae could actually produce the conditions required. Neutron star mergers provide exactly such an environment, and GW 170817 demonstrated this directly. When two neutron stars collide, some of their neutron-rich matter is ejected into space before the remnant, which in this case appears to have collapsed into a black hole based on the mass involved, settles into its final state. This ejected material, blasted outward at a significant fraction of the speed of light, undergoes rapid neutron capture as it expands and cools, creating heavy elements in abundance. The process happens extraordinarily quickly. In the first few seconds after the merger, free neutrons in the expanding debris are captured by seed nuclei, building up atomic mass numbers. The freshly synthesized nuclei are radioactive, undergoing alpha and beta decay as they settle toward stable configurations. This radioactive decay releases energy, heating the expanding debris cloud and causing it to glow. The resulting light is called a kilonova, and its brightness and color evolution depend on the specific mix of elements produced. Spectroscopic observations of the kilonova from GW 170817 confirmed the presence of these heavy elements. The distinctive signatures of strontium and other R process elements were identified in the expanding debris cloud by multiple independent teams using telescopes around the world. The spectra showed absorption features matching the complex atomic transitions of freshly synthesized heavy elements, features that had never been observed anywhere else. Based on the brightness and color evolution, astronomers estimated that the merger produced thousands of Earth masses of heavy elements. Current models suggest roughly 16,000 Earth masses of various elements, including what could be around 10 Earth masses worth of gold and platinum. To put this in perspective, all the gold ever mined on Earth throughout human history amounts to roughly 200,000 tons, about the mass of a single supertanker. A single neutron star merger, if these estimates are accurate, produces about 60 trillion tons of gold. This discovery had profound implications. Much of the gold in the jewelry you might wear, the platinum in catalytic converters, the uranium that powers nuclear reactors. These elements could well have formed in neutron star mergers billions of years ago, before our solar system existed. Based on what we can infer from the rate of such mergers combined with their heavy element yields, neutron star collisions appear to be a major source, possibly the dominant source, of our process elements in the universe. The atoms were scattered through space, eventually incorporated into the gas cloud that collapsed to form our sun and planets, and ultimately became part of everything around us. When you wear a gold ring, you may be wearing material forged in the collision of two neutron stars that occurred before the sun was born. GW 170817 also confirmed the long-suspected connection between neutron star mergers and short gamma-ray bursts. The gamma rays most likely came from a jet of material blasted outward at nearly the speed of light along the axis of the merger. Based on the relative weakness of the observed burst compared to typical short gamma-ray bursts, the data suggests we were viewing the jet slightly off-axis. Had we been viewing directly along the jet, it would have appeared far more luminous. The combined gravitational wave and electromagnetic observations allowed an entirely new kind of measurement. Gravitational waves from a binary inspiral encode information about the distance to the source. The amplitude of the waves depends on both the mass of the merging objects and their distance. By analyzing the gravitational wave signal, scientists determined that the source was about 130 million light-years away. Meanwhile, observations of the host galaxy, NGC 4993, allowed measurement of the galaxy's recession velocity due to the expansion of the universe. Combining these measurements gave an independent estimate of the Hubble constant, the rate at which the universe is expanding. This marked the birth of what astronomers call standard sirens. Just as standard candles are astronomical objects of known luminosity used to measure distances, standard sirens are gravitational wave sources of known gravitational wave strength. The technique promises to help resolve ongoing disputes about the exact value of the Hubble constant, a measurement that has shown frustrating discrepancies when made using different methods. Multi-messenger astronomy, the observation of cosmic events using both gravitational waves and electromagnetic radiation, had been transformed from theoretical possibility to practical reality. Each messenger carries different information. Gravitational waves reveal mass, spin, and orbital dynamics. Electromagnetic observations show temperature, composition, and environment. Together they provide a far more complete picture than either could alone. Part 7. The Orchestra of Detectors. To understand how gravitational wave detection has evolved since that first discovery, we need to appreciate the global network of instruments now search in the cosmos and how they work together to locate and characterize sources. The basic principle remains the same as Weiss originally envisioned: laser interferometry. A laser beam is split, sent down two perpendicular paths, reflected back, and recombined. Any difference in path length causes an interference pattern shift that can be measured with exquisite precision. But the engineering details make all the difference between a laboratory demonstration and an instrument capable of detecting cosmic collisions. The LIGO detectors each have arms 4 kilometers long, housed in vacuum tubes that stretch across the landscape. At LIGO Livingston, the arms extend across Louisiana pine forests. At LIGO Hanford, they cross the desert of eastern Washington. The vacuum inside the tubes is about 1 trillionth of atmospheric pressure, emptier than the space between planets, to prevent air molecules from scattering the laser light. At the ends of each arm are test masses, mirrors made from ultra-pure fused silica, about 40 kilograms each, polished to near atomic smoothness. These mirrors must be almost perfectly still. Any random motion larger than the gravitational wave signal will mask the detection. To achieve this, the mirrors are suspended on a series of pendulums, each stage filtering out vibrations. The final suspension uses glass fibers fused to the mirror substrate, minimizing thermal noise. Active seismic isolation systems take the filtering further. Sensors detect ground motion in real time, and computer-controlled actuators apply counterforces to cancel the vibrations before they reach the mirrors. The combination of passive and active isolation reduces ground motion by a factor of about 1 billion at the frequencies where gravitational wave signals are expected. The laser system has evolved significantly since initial LIGO. Advanced LIGO uses a 200-watt continuous wave laser, derived from the same neodymium-doped yttrium aluminum garnet technology used in many industrial and scientific lasers. But the raw laser beam isn't good enough. It passes through multiple stages of stabilization to reduce fluctuations in power and frequency. The resulting beam is among the most stable ever created. Inside the interferometer, the light bounces between mirrors about 280 times before recombining, effectively increasing the arm length by that factor. Additional power recycling mirrors send light that would otherwise be lost back into the interferometer, boosting the effective laser power. Signal recycling mirrors further enhance sensitivity at specific frequencies where signals are expected. The Virgo detector in Italy operates on similar principles with 3-kilometer arms. Virgo is operated by the European Gravitational Observatory Consortium, involving France, Italy, the Netherlands, Poland, Spain, and Hungary. Joining the network after LIGO began operation, Virgo adds a third perspective that dramatically improves source localization. With 2 detectors, you can narrow down a source to an arc across the sky. With 3, you can pinpoint a specific location. Japan's Kagra detector, built underground in the Kamioka mine to reduce seismic noise, has 3-kilometer arms and uses cryogenically cooled sapphire mirrors to reduce thermal noise. Kagra joined the international network in 2020, though it is still working to reach its design sensitivity. Plans exist for additional detectors. LIGO India, currently under construction, will add another intercontinental baseline, further improving localization. The more detectors operating simultaneously, the better astronomers can determine where gravitational wave signals originate, and the more confident they can be that a detection is real rather than instrumental noise. The cumulative observations have grown dramatically. Between the first detection in September 2015 and early 2024, the network has detected roughly 300 gravitational wave events. The vast majority are binary black hole mergers, but the catalog also includes binary neutron star mergers, mixed black hole neutron star mergers, and some events whose precise nature remains uncertain. Each detection adds to our statistical understanding. The masses of mergent black holes span a wide range, from about 5 solar masses to over 100 solar masses. Some systems involve black holes spinning rapidly, while others spin slowly or not at all. Based on current observations, The merger rate suggests that binary black hole mergers likely occur somewhere in the observable universe every few minutes. We detect only a tiny fraction, those close enough and oriented favorably enough for their signals to exceed our detection threshold. The spin measurements are particularly interesting. When two black holes merge, the final black hole carries angular momentum contributed by the original black hole's spins and their orbital motion. By analyzing the gravitational wave signal, scientists can infer the spin of the final black hole. These measurements are beginning to constrain theories of how massive stellar binaries evolve and how black holes form, though the sample size is still growing and conclusions remain preliminary. Some detections have challenged existing models. GW190521, detected in May 2019, involved two black holes with masses of about 85 and 66 solar masses, merging to form a black hole of about 142 solar masses. The heavier component lies in the pair instability gap, a range of masses where stellar evolution theory suggests black holes should not form through ordinary stellar collapse. Various explanations have been proposed. The black hole might have formed through a previous merger, or the progenitor star might have evolved in unusual conditions. The presence of black holes in this mass range appears to suggest formation pathways beyond what standard models predicted, though our understanding of these extreme objects continues to evolve as more observations accumulate. Part 8. The Cosmic Hum. While LIGO and its partners listen for individual gravitational wave events at frequencies of tens to thousands of hertz, another approach is opening a window on much lower frequencies, pulsar timing arrays. The concept builds on the same precision timing that made the Hulse-Taylor binary pulsar so valuable. Millisecond pulsars, neutron stars spinning hundreds of times per second, produce extraordinarily regular radio pulses. If you know when each pulse should arrive, any deviation from that expectation reveals something interesting, perhaps a planet orbiting the pulsar, or perturbations from passing objects, or the stretching and squeezing of space-time by gravitational waves. Gravitational waves at nanohertz frequencies, with periods of years to decades, would cause subtle correlations in the timing of pulsars scattered across the sky. A wave passing through the Milky Way would stretch spacetime in one direction while compressing it in the perpendicular direction. Pulsars in the stretching direction would have their pulses arrive slightly late, while those in the compressing direction would have pulses arrive slightly early. The effect is minuscule, on the order of hundreds of nanoseconds accumulated over years, but with enough pulsars observed precisely enough for long enough, it becomes detectable. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, was founded in 2007 to pursue this approach. The collaboration brought together pulsar astronomers from across the United States and Canada, pooling their expertise and telescope time. Similar collaborations formed in Europe, where the European Pulsar Timing Array, or EPTA, combined resources from the United Kingdom, Germany, France, the Netherlands, and Italy. In Australia, the Bayer Parkes Pulsar Timing Array, or PPTA, used the iconic 64-meter Parkes Radio Telescope to monitor Southern Hemisphere pulsars. In China, the Chinese Pulsar Timing Array, or CPTA, began observations with the 500-meter Aperture Spherical Telescope, the world's largest filled aperture radio telescope. These groups eventually joined together as the International Pulsar Timing Array Consortium, sharing data and analysis techniques while pursuing complementary observations. The challenges are formidable and quite different from those facing LIGO. Individual pulsars have their own timing quirks, glitches where the rotation rate suddenly changes due to internal rearrangements of the neutron star's crust, long-term spin down as the pulsar loses energy through magnetic dipole radiation, and various other noise sources related to the pulsar's emission mechanism. The interstellar medium between us and the pulsars causes radio pulse delays that vary with time and frequency as the radio waves travel through ionized gas. Solar wind from our own sun can introduce additional time-varying delays. Isolating the tiny gravitational wave signal from all these effects requires sophisticated analysis methods and years of patient observation. Nanograv's approach has been to monitor dozens of millisecond pulsars with the world's largest radio telescopes. The Green Bank Telescope in West Virginia, with its 100-meter dish, making it the world's largest fully steerable radio telescope. The now collapsed Arecibo Observatory in Puerto Rico, which for decades was the world's largest single-dish telescope, and the Very Large Array in New Mexico, a collection of 27 radio antennas that can be combined for enhanced sensitivity. Each pulsar is observed roughly every 2 weeks, building up timing baselines that now extend over 15 years. The data analysis is painstaking. For each observation, astronomers must determine the precise arrival time of each pulse, accounting for the telescope's motion around the Earth, Earth's motion around the Sun, and the Sun's motion through the galaxy. They must correct for dispersive delays caused by the interstellar medium, effects that change with the radio frequency being observed. They must model each pulsar's intrinsic spin down and any irregular behavior. What remains after all these corrections, the residual timing variations, could potentially contain the signature of gravitational waves. In June 2023, Nanograv announced a breakthrough: evidence for a gravitational wave background permeating the universe. Using 15 years of data from 67 pulsars, they detected the distinctive pattern of correlations predicted by gravitational wave theory. The announcement sent ripples through the astronomical community, as this represented an entirely new frequency window on the gravitational wave universe. The key signature is called the Hellingsdowns curve, named after the physicists who predicted it in 1983. It describes how the correlation between timing residuals from different pulsars should depend on the angular separation between them in the sky. Pulsars close together should be affected similarly by passing gravitational waves, and thus show positive correlation. Pulsars separated by about 90 degrees should show negative correlation. The specific shape of this curve is a unique fingerprint of gravitational waves, distinguishing them from other noise sources. Nanograv's data showed correlations matching the Hellingsdowns curve with a statistical significance between 3 and 4.6 sigma, depending on the analysis method. While not quite at the 5 sigma threshold traditionally required to claim discovery in physics, this was strong evidence. Crucially, the same month saw similar announcements from EPTA, PPTA, and CPTA, with each collaboration independently finding consistent results. The agreement across independent datasets using different telescopes and analysis methods made the case compelling. What creates this gravitational wave background? The leading explanation involves supermassive black holes, the monsters at the centers of galaxies that can contain billions of solar masses. When galaxies merge, as they frequently do throughout cosmic history, their central black holes eventually find each other and begin orbiting together. As they spiral closer, they emit gravitational waves at nanohertz frequencies, exactly what pulsar timing arrays are sensitive to. This interpretation aligns well with our understanding of galaxy evolution. Simulations suggest that the background is most likely the superposition of signals from hundreds of thousands or millions of supermassive black hole binaries scattered throughout the observable universe, each contributing gravitational waves at slightly different frequencies. The overlapping signals create a stochastic background, similar to the murmur of many distant conversations, blending into an undifferentiated hum. Based on the observed signal strength and our understanding of galaxy merger rates, the supermassive black hole explanation appears consistent with expectations, though significant uncertainties remain. Alternative explanations have been proposed. Cosmic strings, primordial black holes formed shortly after the Big Bang, or exotic phase transitions in the early universe. Future observations should help distinguish between these possibilities. If the background comes from supermassive black hole binaries, as seems most likely, we should eventually begin to resolve individual sources. The closest or most massive binaries contributing disproportionately to the signal. The nanohertz gravitational wave universe, revealed by pulsar timing arrays, complements the stellar mass universe, observed by LIGO and Virgo. The two windows probe completely different sources and physics. Together they give us a much more complete picture of how gravity shapes the cosmos on scales from stellar remnants to the largest structures in existence. Part 9. The future of gravitational wave astronomy. The detectors operating today represent only the beginning. Over the coming decades, new instruments will extend our reach across the gravitational wave spectrum, revealing phenomena we can barely imagine today. The most ambitious near-term project is LISA, the Laser Interferometer Space Antenna. LISA will place 3 spacecraft in orbit around the Sun, trailing Earth by about 50 million kilometers. The spacecraft will form a triangle, with each side measuring 2.5 million kilometers, more than 6 times the distance from Earth to the Moon. Laser beams will travel between the spacecraft, forming a gravitational wave detector of unprecedented scale. The concept for LISA originated in the 1980s, when it became clear that ground-based detectors would never be able to access certain frequency ranges. Seismic noise from Earth limits how low in frequency ground-based detectors can operate. Below about 10 Hz, ground motion overwhelms any possible gravitational wave signal, no matter how sophisticated the isolation systems. Yet many important gravitational wave sources emit primarily at lower frequencies, in the millihertz range, where orbital periods are measured in minutes to hours rather than milliseconds. Space-based detection offers several advantages. There are no seismic vibrations to filter out, no earthly disturbances to contend with. The spacecraft float freely in interplanetary space, affected only by gravitational forces and the occasional impact of a dust particle. The long arm lengths make LISA sensitive to gravitational waves at much lower frequencies than ground-based detectors, from about 0.1 millihertz to 100 millihertz. This frequency band is rich with sources that ground-based detectors cannot observe. The engineering challenges of LISA are formidable, but different from those facing LIGO. The spacecraft must maintain their relative positions to extraordinary precision, even though they are separated by millions of kilometers, and each affected slightly differently by the sun's gravity and radiation pressure. The laser beams traveling between spacecraft diverge over such vast distances, arriving as faint signals that must be carefully collected and measured. Temperature fluctuations caused by changing solar illumination must be controlled or accounted for. And unlike ground-based detectors, LISA cannot be adjusted or repaired once launched. Everything must work correctly the first time. LISA will detect mergers of supermassive black holes, the same sources responsible for the pulsar timing array background, but at a later stage in their evolution when they're closer to merger and emitting at higher frequencies. These observations will reveal how supermassive black holes grow and how galaxy mergers proceed. Based on what we know about galaxy evolution and the abundance of supermassive black holes, LISA could potentially observe mergers involving black holes millions or billions of times the mass of the Sun from vast distances across the observable universe. Such events, if detected, would provide windows into the earliest epochs of cosmic history, when the first galaxies were forming and their central black holes were beginning their growth. LISA will also observe compact binaries in our own galaxy, pairs of white dwarfs, neutron stars, and stellar mass black holes that are orbiting too slowly to be detected by LIGO. Thousands of these verification binaries are already known from electromagnetic observations and will serve to calibrate LISA's performance. Many more will be discovered, providing a detailed census of compact objects in the Milky Way. Based on population models of our galaxy, LISA is expected to detect so many galactic binaries that their combined signals will form a continuous confusion noise at certain frequencies, a chorus of millions of binary systems, all contributing to the detector output simultaneously. Perhaps most excitingly, LISA will observe extreme mass ratio in spirals, small compact objects spiraling into supermassive black holes. These events occur when a stellar mass black hole, neutron star, or white dwarf wanders too close to the supermassive black hole at a galaxy's center and becomes captured into a decaying orbit. As the smaller object slowly falls into the larger black hole, it traces out a complex orbit that maps the space-time geometry around the larger black hole with exquisite precision. The gravitational wave signal encodes this map, allowing precision tests of general relativity in the strongest possible gravitational fields. Any deviation from Einstein's predictions would be revolutionary, potentially pointing toward new physics beyond general relativity, though current theory provides no strong reason to expect such deviations. LISA is a joint project of the European Space Agency and NASA, with launch currently planned for the mid-2030s and 30s. The technology has been proven by LISA Pathfinder, a test mission launched in 2015 that demonstrated the required precision for spacecraft positioning and acceleration control. LISA Pathfinder showed that two test masses inside a spacecraft could be kept in nearly perfect free fall, affected only by gravity, to an accuracy far exceeding the mission requirements. This success gave the scientific community confidence that the full LISA mission is technically feasible. On the ground, even more sensitive detectors are being planned. The Einstein telescope is a proposed European project that would build a triangular underground detector with arms 10 kilometers long. Going underground reduces seismic noise. The triangular configuration allows detection of all gravitational wave polarizations and provides better directional sensitivity. Cryogenic mirrors, cooled to just a few degrees above absolute zero, would reduce thermal noise far below what current detectors achieve. In the United States, Cosmic Explorer is a proposed detector with arms 40 kilometers long, 10 times the length of LIGO. The increased arm length would improve sensitivity proportionally, allowing detection of binary black hole mergers across most of the observable universe. Some merger events that LIGO can barely detect would stand out dramatically in Cosmic Explorer data. Both Einstein Telescope and Cosmic Explorer are aiming for operation in the 2030s, though funding and construction timelines remain uncertain. If built, these detectors could increase the detection rate by factors of thousands, from dozens of events per year to what simulations suggest might be dozens per day. The statistical power of such large catalogs would enable precision measurements of black hole populations, tests of general relativity in extreme conditions, and insights into stellar evolution and cosmology that we can currently only imagine. At the highest frequencies, above the range of LIGO, other detection methods are being explored. Resonant cavity detectors might detect gravitational waves from exotic sources, like cosmic strings or primordial black holes evaporating through Hawking radiation. These high-frequency waves would have such short wavelengths that tabletop experiments could become sensitive to them, though such sources remain theoretical predictions that have yet to be confirmed observationally. The ultimate prize, still likely beyond the reach of any planned detector, would be gravitational waves from the Big Bang itself. Just as the cosmic microwave background provides a snapshot of the universe when it was 380,000 years old, primordial gravitational waves would carry information from far earlier epochs, perhaps from the first fraction of a second after the Big Bang. According to inflationary theory, the rapid expansion thought to have occurred in the universe's earliest moments should have generated gravitational waves that persist today as a faint background. Detecting this background would provide direct evidence about conditions when the universe was younger than any other observation can probe. Based on our theoretical understanding of the early universe, these primordial waves could imprint subtle patterns on the cosmic microwave background polarization. Current and future microwave observations are searching for these patterns. LISA might also be sensitive to certain models of the inflationary gravitational wave background, but the predicted signal is extraordinarily faint, and definitive detection may require technology that hasn't yet been invented. Part 10. A New Era of Cosmic Exploration. We've journeyed from Einstein's theoretical insight in 1916 to the global network of gravitational wave detectors operating today. We've explored the decades of struggle, the false starts and controversies, the incremental progress, and the sudden breakthroughs that mark the history of any great scientific enterprise. We've seen how gravitational waves have already transformed our understanding of black holes, neutron stars, and the violent processes that shape the universe. But in a deeper sense, we're still at the very beginning. Gravitational wave astronomy is barely a decade old. The most sensitive detectors yet built have observed only a tiny fraction of the universe's gravitational wave sources. Every improvement in sensitivity, every new detector added to the network, every new frequency band open for observation reveals phenomena we hadn't imagined. Consider what we've learned already. Black holes appear to be more abundant and more diverse than earlier models suggested. They merge frequently, and when they do, they convert significant fractions of their mass into gravitational wave energy. Neutron star mergers produce the heavy elements that enrich the universe, the same elements that eventually form into planets and life. The cosmos is permeated by a gravitational wave background, a constant hum of spacetime, rippling from what we believe to be millions of supermassive black hole binaries slowly spiraling together across the universe. Consider what we might learn in the coming decades. How do supermassive black holes form and grow? What happens in the final moments before two neutron stars merge? Could there be exotic objects like cosmic strings or primordial black holes lurking in the gravitational wave sky? What might gravitational waves tell us about the earliest moments after the Big Bang? The universe has been sending us gravitational wave signals since the beginning of time. Every cataclysmic event, every merger and explosion and collapse has rippled outward through space-time at the speed of light. These signals pass through us constantly, stretching and squeezing the space between our atoms by amounts far too small to feel. But now finally, we have instruments sensitive enough to detect them. When you look up at the night sky, you see light from distant stars and galaxies. That light carries information about the universe, but it's information filtered by the electromagnetic processes that emit, scatter, and absorb radiation. Gravitational waves carry different information unfiltered by these processes. They come directly from the most violent events in the cosmos, carrying the signatures of space-time itself, being warped by extreme concentrations of mass and energy. We have gained a new sense with which to experience the universe. For the first time in history, we can hear the cosmos as well as see it. The invisible symphony that Einstein predicted more than a century ago is now playing for anyone willing to listen. Thank you for joining me on this exploration of gravitational waves and the remarkable human quest to detect them. If you enjoyed this journey through one of science's greatest achievements, please consider liking and subscribing to support the channel. Your engagement helps me continue creating these deep explorations of the cosmos and our place within it. Until next time, keep wondering about the universe. Keep asking questions, and remember that somewhere out there, right now, black holes are merging, neutron stars are colliding, and gravitational waves are rippling across the cosmos, carrying stories of destruction and creation that are only now becoming audible to human ears. Good night.